We live on a small, rocky world bathed in the light of a single star. For millennia, we have looked up at the night sky and wondered what's out there. Are we alone? How did it all begin? To answer these grand questions, we build tools, telescopes, that act as our extended eyes, letting us peer deeper into the cosmic ocean. The James Webb Space Telescope, or JWST, is our newest, most powerful eye on the universe. It's a marvel of engineering sent 1,000,000 miles from Earth to look back in time and unveil the secrets of the cosmos. Unlike Hubble, which sees mostly invisible light, Webb is designed to see in infrared. Think of infrared as heat vision. It allows Webb to pierce thick clouds of gas and dust that hide newborn stars and planets. Ancient light from the first galaxies has been stretched by expansion into the infrared part of the spectrum. Today is November 24th, 2025, and Webb has already been rewriting the textbooks. It's a revolution in progress, pixel by pixel, as data streams back to Earth. One of the most profound questions we can ask is how our own solar system came to be. We see Jupiter with its dozens of moons, Saturn with its glorious rings. How did they get there? Webb aimed at CT-Cha-B, an exoplanet 625 light-years away, and found a swirling disk of gas and dust around the planet itself. It's a potential moon-forming disk. This wasn't just a blurry image. Webb analyzed the disk's chemistry. Webb detected the signatures of diacetylene, hydrogen cyanide, propyne, benzene, a carbon-rich recipe for making moons. It's like looking at a construction site and seeing the piles of lumber, bricks, and pipes. The same physical laws that built our moon and the moons of Jupiter and Saturn could be at work across the galaxy. Imagine CT-Cha-B slowly gathering its disk, clumping over millions of years into one or several brand new moons. Key fact: the first direct measurement of a circumplanetary disk's composition. We're no longer just planet hunters. We're officially on the hunt for exomoons, and Webb is leading the charge. Finding planets around other stars is tricky. Most of the time, we find them indirectly. We see a star dim slightly as a planet crosses, or we see the star wobble from a planet's tug. Taking an actual picture is like spotting a firefly next to a brilliant searchlight. But Webb's advanced optics and infrared sensitivity managed to do just that. Webb potentially captured its first direct image discovery, a Saturn-mass world around the young star TWA7, the lightest planet ever seen with this technique. It orbits about 52 times farther than Earth is from the Sun, helping separate the planet's glow from its star. This is a technical triumph. Direct imaging is the holy grail for exoplanet hunters. By catching the planet's own light, we can probe its atmosphere, temperature, even clouds. This is how we will eventually search for signs of life, by reading chemical fingerprints. Webb's success opens a new frontier, a growing gallery of family portraits from other solar systems. The universe we see, stars, galaxies, planets, and us, is only a tiny fraction of what's out there. About 85% of all matter is dark matter. It doesn't shine, doesn't reflect light, doesn't interact with normal matter, except through gravity. We know it's there because it bends light and holds galaxies together. So how do you map the invisible? You get creative. Webb teamed up with Chandra. Webb measured lensing, gravity's distortions, to weigh total mass. Chandra mapped superheated gas and X-rays. Subtract the stars, subtract the hot gas. From the total mass, what's left is dark matter. Released June 30th, 2025. A stunning visualization of the universe's invisible scaffolding. More than a pretty picture, these maps test theories. Does dark matter clump as predicted? Interact with itself? It's like seeing the foundations and support beams, the cosmos's architectural plan. One of Webb's primary missions is to be a time machine, because light takes time to travel. Webb was built to see the universe in its infancy, and it has already exceeded expectations. Using NIR spec, astronomers measured a record-breaking galaxy with redshift about 14, seen only 290 million years after the Big Bang. An infant universe compared to today's 13.8 billion years. Seeing such a galaxy is like finding a fossil from the dawn of life on Earth. Webb studied GNZ11, which existed when the universe was about 430 million years old, and found a rapidly feeding supermassive black hole at its center. This challenges models, hinting some black holes may form by direct collapse of massive gas clouds rather than slow growth from dead stars. These discoveries are fundamental. They are giving us women the di iga kuaijiao of how the universe became the complex, star-filled place it is today. Before Webb, this era was mostly theoretical. Now, we have data, spectra, elements, and even the monster black holes lurking at galactic hearts. A new kind of archaeology. Our artifacts are galaxies from the beginning of time. Section 6. Cosmic orphans. Rogue planets with their own systems. We tend to think of planets as belonging to a star, but the universe is chaotic, and some planets are hurled into interstellar space. These free-floating worlds drift alone, seemingly cold and dead. Webb surveyed a group of rogue giants with masses around Jupiter's, and found something astonishing. 6 were surrounded by their own disks of warm dust and gas, miniature protoplanetary disks. Digging deeper, Webb found the spectral signature of silicate grains, the building blocks of rock. Finding them crystallizing is the first step toward forming rocky worlds. Earth, Venus, Mars. These rogue planets could be forming their own families of smaller worlds, racing through space with no star. Could such a system harbor life? It's a long shot, no sun for warmth, but it forces us to think outside the box about where habitable niches might exist. Section 7. A symphony of newborn stars. The aligned jets of Serpens. Star birth is messy, violent, and beautiful. Deep in dense clouds, gravity pulls gas and dust together until a new star ignites. Infant stars blast out narrow jets. When they strike the nebula, they create glowing outflows. Webb found a whole group of outflows in Serpens, but all tilted the same way, like sleet pouring down in a storm. This implies a larger, unseen influence, magnetic fields or cloud-scale rotation, an invisible conductor leading the orchestra of newborn stars. Most stars, including our Sun, are born in groups. Understanding these forces helps explain our own beginnings. Section 8. Ingredients for life. Water, carbon, cosmic building blocks. Webb found water ice in a band of icy bodies around the star HD 181327, 156 light-years away, a Kuiper Belt analog. Such reservoirs can deliver water to young worlds, as happened on early Earth. Webb also detected a massive cloud of carbon in the very early universe, pushing back when life's ingredients could first appear. Carbon, the basis of our biology, was present. 这是在宇宙黎明时，微波正在向我们展示，宇宙已经准备好迎接生命很长一段时间了。我们还没有发现生命，但我们正在发现生命所需的一切都在那里，等待着合适的条件出现。Section 9. The Cold Giant, the Butterfly's Heart. A Gallery of Wonders. Webb peered through dust to reveal the core of the Butterfly Nebula, a dense torus and sculpting jets shaping its delicate wings. Webb studied 14 Hercules C, roughly 7 Jupiter masses, yet a cosmic cold spot at about 26 degrees Fahrenheit. This expands our catalog's diversity and helps test how planets form and evolve. From moon-forming disks to the earliest galaxies to dark matter scaffolding, Webb is filling in the cosmic story. In a short time, it has confirmed some theories, shattered others, and opened entirely new avenues of research. Its data will be studied for decades, leading to discoveries we can't yet imagine. The James Webb Space Telescope has given humanity a new set of eyes, and the universe is just starting to show what it's been hiding. The best is yet to come.